Hello. We have been discussing a Sommerfeld model where electrons are treated not as the gas molecules of ideal gas, rather they are treated as indistinguishable particles, that is identical particles, and Pauli exclusion principle comes into effect, and we have Fermi-Dirac statistics that these particles, that is electrons or any other fermions, that obey. We have derived the Fermi distribution function, the Fermi-Dirac distribution function, and now we are going to discuss the thermal properties of the free electron gas. So, as we know, the energy of the free electron gas particles, that is epsilon, a function of k, is given as h cross squared k squared over twice m, where k is the wave vector, the crystal momentum, and m is the mass. We first verify that the distribution function is consistent with the ground state properties that we have derived earlier. Ground state means the temperature equals 0. So, at absolute 0 temperature, the states that we have that are with energy less than or equal to the Fermi energy. Fermi energy is the maximum possible value of the energy for these electrons at absolute 0 temperature. Now, the states with energy less than or equal to Fermi energy, they are all occupied, and higher energy states are completely empty. So, in this kind of a situation, the probability of a state being occupied is 1, provided the energy eigenvalue corresponding to that state is less than the Fermi energy, and this is 0 provided the energy eigenvalue associated with that state is greater than the Fermi energy. This is valid at absolute 0 temperature. Now, on the other hand, if we consider the limit that temperature tends to 0, if we consider the Fermi-Dirac distribution function here, that is limit temperature tends to 0 f k s, this quantity equals 1 provided epsilon is less than the chemical potential. That is denoted as mu, and this quantity is 0 provided epsilon, that is a function of the momentum, certainly is greater than the chemical potential mu. That you can find from the expression of the Fermi function that we have derived earlier. Now, if we have to satisfy this and this together, both of these can be simultaneously satisfied only if we have limit temperature tends to 0, mu in that limit equals the Fermi energy. Only then it is possible to satisfy both these conditions. So, this is necessary. So we know that at temperature tending to 0, the chemical potential is equal to the Fermi energy, and I can tell you that for metals, the chemical potential and the Fermi energy, they remain almost same even at higher temperatures. So the most important application of this Fermi-Dirac statistics is the calculation of the electronic contribution to the constant volume specific heat of a metal. Specific heat at a constant volume. CV. So how do we define CV? CV is statistically defined as T over V del S del T at constant volume. This comes from statistical mechanics, equals del small u del T at constant volume. What is small u? Small u is the internal energy per unit volume. Now, if we perform independent electron approximation, we can write the internal energy as sum over K epsilon times K, epsilon a function of K times the Fermi function in terms of energy. So this gives us the Fermi function gives us the probability of a particular energy level being occupied by electron, and this is the corresponding energy. Summed over this is the internal energy with a factor of 2 that comes from the spin degeneracy. So we have introduced the Fermi function to emphasize that the probability depends on K through the electronic energy E, and in this form we can write the Fermi function as 1 over e power epsilon minus mu over kBt plus 1, just what we have derived earlier. Now, if we divide both sides of this equation by the volume, then what do we get? We get u, small u, equals integration, we are converting the sum into an integral, d3k over 4 pi cubed epsilon a function of k f epsilon k. This is what we find. So if we want to evaluate the total number of electrons, that can be given as capital N equals sum over I Fi, the Fermi distribution function, equals sum over I 1 over e power epsilon I minus mu over kBt plus 1. and small n, that is the density of electrons, the number of electrons per unit volume, is given as, converting the sum into integral form, d3k over 4 pi squared f, that's a function of energy and momentum through energy. We need to evaluate this integral, which is, so it's of the form integral d3k over 4 pi cubed any function f, arbitrary function, not necessarily the Fermi function. So we are now talking about this form of the integral, and once we learn how to solve this form of integral, we will apply that for Fermi function to evaluate this quantity here. Okay. So epsilon here, as we know, is h cross squared k squared over twice m. So the k dependence is spherically symmetric, and provided the k dependence is spherically symmetric, we can write integration over d3k divided by 4 pi cubed f, which is a function of epsilon k. This equals integration from 0 to infinity k squared dk over pi squared f epsilon k. This can be written as integration from minus infinity to infinity dE g epsilon f epsilon, d epsilon g epsilon f epsilon. So we are converting the range of the integral from 0 to infinity to minus infinity to infinity. How? And we have introduced something new here, g, that's a function of epsilon. So what is g as a function of epsilon? Here, if we see how this quantity is introduced, how this is replaced this way, and the differential of energy has been brought, considering that, comparing these two equations, we can write g epsilon as m over h cross squared pi squared twice m epsilon over h cross squared square root of this quantity, provided epsilon is greater than 0 and this quantity g equals 0 if epsilon is less than 0. This is how we define this quantity GE. Now what is this quantity? If we examine the form of the integral, we can say that G epsilon d epsilon that is the differential, this gives us per unit volume the number of single electron levels in the energy range epsilon to epsilon plus d epsilon. This is what it means. And if that is the case, then we can give a concrete name, a handy name to this quantity G epsilon, the density of levels per unit volume. Often called as the density of states. Now, we can also write this quantity, the density of levels, as 3 over 2 n over the Fermi energy epsilon f, epsilon over epsilon f power 1 by 2 if epsilon greater than 0 and this quantity equals 0 if epsilon is less than 0. We have already defined epsilon f and kf. Those are defined at absolute 0 temperature. Now, a quantity of particular numerical importance would be the density of levels at the Fermi energy. So, if we put Fermi energy here, we will get Fermi energy here. So, that will give us density of levels at the Fermi energy. This can be expressed as m times kf over h cross squared pi squared, which is 3 over 2 n over epsilon f. This is what we will get. So, here we have seen that the density of states for 3 dimension goes for independent electron model metals as the energy power half for positive energies. A homework for you would be to find out the density of states in 1-dimensional metal and 2-dimensional metal, how it depends on energy. Okay. After finding out the meaning of the G epsilon, we can now rewrite the internal energy per unit volume as minus infinity to infinity, because the negative energies are not going to contribute anything. Our G epsilon is 0 for negative energies. So, we can extend the integration limit to minus infinity, and anyway the upper limit was plus infinity. D epsilon G epsilon, and then epsilon itself, the energy, times the Fermi function. This is going to give us the internal energy per unit volume and the number of electrons per unit volume, that can be expressed as minus infinity to infinity d epsilon G epsilon Fermi function times Fermi function, which is a function of the epsilon. Now, let's plot the Fermi function. How do we plot the Fermi function? Let's consider Fermi function at different temperatures. At this axis, we plot the energy epsilon. So, we are considering different temperatures. Here we are plotting the Fermi function at temperature equals 0. And if we have, say, this as the chemical potential. Then at 0 temperature, the Fermi function, say, is 1 here, will look like this, this, this at absolute 0 temperature. But if we have the temperature greater than 0, then it would look somewhat different. If this point is 1, then it would go somewhat like this. At finite temperature. And this width is delta epsilon. So delta epsilon is nearly equal to Boltzmann constant times the temperature. Now let us consider a generic function h epsilon, a generic function, and we consider its Taylor expansion about epsilon equals mu. So h epsilon would be given as sum over n equals 0 to infinity. This n is the index, this is not the number density of the electrons. D order n, so it's the order of the derivative actually. D epsilon order n h epsilon, and here we set epsilon equals mu, and the coefficient to this quantity would be epsilon minus mu power n over n factorial. This is the Taylor expansion. So if we now integrate over h, that's a function of epsilon, multiplied by the Fermi function, we would get minus infinity to infinity h epsilon Fermi function, which is a function of epsilon, d epsilon. This quantity equals minus infinity to mu h epsilon d epsilon plus sum over n equals 1 to infinity. So n equals 0 term is this term here, and then sum over n equals 1 to infinity is remaining, kb t power twice n a n d twice n minus 1 d epsilon twice n minus 1 h epsilon, putting the value epsilon equals mu. If we now simplify this further, we can write this quantity equals minus infinity to mu h epsilon d epsilon plus pi squared over 6 kb t squared h prime, that is the first order derivative of mu, plus 7 pi power 4 over 360 kb t power 4 h triple prime mu plus something of the order of kb t over mu power 6. Now, if we want to evaluate the specific heat of a metal at a given temperature, the temperature is small compared to the Fermi temperature. What is Fermi temperature? Tf is given as epsilon f over the Boltzmann constant. Now, our temperature is T, which is less than or a lot less than the Fermi temperature. Our temperature is much smaller compared to the Fermi temperature. Under that kind of a situation, we can use this Taylor expansion to write the internal energy per unit volume as integration over 0 to mu epsilon g epsilon d epsilon plus pi squared over 6 kb t squared mu g prime mu plus g mu plus something of the order of temperature power 4 and the number density as integration 0 to mu g epsilon d epsilon plus pi squared over 6 kb t squared g prime mu plus some term where the temperature power 4, that order term is there. So, if we want to be correct up to temperature square terms, T squared terms, we can write integration 0 to mu h epsilon d epsilon equals integration 0 to epsilon f, the Fermi energy, h epsilon d epsilon plus mu minus epsilon f h epsilon f. This is correct. So, this is correct up to the second order, second power of the temperature. Now, if we apply this for the internal energy per unit volume, we can write small u equals integration from 0 to epsilon f epsilon g epsilon d epsilon plus epsilon f mu minus epsilon f g epsilon f plus pi squared over 6 kb t squared g prime epsilon f plus pi squared over 6 kb t squared g epsilon f plus terms of the order of temperature power 4. Similarly, the number density can be expressed as 0 to epsilon f, the Fermi energy, g epsilon d epsilon plus mu minus epsilon f g epsilon f plus pi squared over 6 kb t squared g prime epsilon f. Since we are calculating the specific heat at constant density, so we have N is independent of temperature. But here in this term we can see that there is a temperature dependence of this density. Now, if we have by definition of Cv, that is the specific heat for a constant density, the temperature is the number density is independent of temperature, then the temperature independent first terms of U and G, they give us the ground state. So, ground state means at 0 temperature, at absolute 0 temperature U is just this and N is just this. When we increase the temperature, N has to still be just this, because N for calculation of Cv cannot be temperature dependent, but U can still be temperature dependent. If N cannot be temperature dependent, then the remaining of the terms, that is these terms here, this must go to 0. In other words, 0 equals mu minus epsilon f g epsilon f plus pi squared over 6 kbt squared g prime epsilon f. This quantity must be 0, and if this quantity happens to be 0, then that gives us the value of mu at a finite temperature as epsilon f minus pi squared over 6 kb t squared g prime epsilon f over g epsilon f. So, this is the expression for the chemical potential as a function of temperature. We have obtained by requiring that N remains unchanged even at higher temperature, because we are calculating Cv. So, if this is the expression for mu, the chemical potential, then, and we know that for free electron the density of levels, this quantity goes as square root of the energy, then we can write mu equals epsilon f 1 minus 1/3 of pi kb T over twice epsilon f squared. And we can see that mu changes very little if we increase the temperature from absolute 0 to room temperature. At room temperature, the change is about 0.01%, just this little. And now if we want to calculate the internal energy per unit volume, that can be given as U0, which is the energy density at ground state. The internal energy per unit volume at absolute 0 temperature is given as U0, the first term in the expression of U here, plus pi squared over 6 kb T squared G function of epsilon f, the density of levels at the Fermi energy. Now the specific heat can be calculated as Cv equals del U del T at constant number density, that is given as pi squared over 3 kb squared T times density of levels at the Fermi energy. And so for free electrons, we can write Cv equals pi squared over 2 kb T over epsilon f times n kb by putting the expression for gf at putting the expression for g at epsilon f in this expression for Cv. So we know the expression for the density of levels for free electron system, and putting that we obtain this, that is the electronic contribution to the specific heat. And if we consider the classical ideal gas, for that Cv equals 3n kb over 2, which is a lot different from this one. There is no concept of Fermi energy for classical ideal gas, and entire thing is very different. We can see that considering indistinguishable particles, Pauli exclusion principle and Fermi-Dirac distribution function, how much it differs, the electronic contribution to the specific heat differs from the classical ideal gas.